Guys, can you see my screen now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So when I plot the graph of this current which is increasing, it looks something like this. Sir, I can't hear you clearly. No problem, Satvik. I'll just make a new lecture. Wait. So on the y-axis we have current, and on the x-axis we have time. And if I say the maximum current is E by L, do you remember this in the last class when we derived this formula? You can see over here, E by R, I is equals to E by R. E by R is basically what? I naught, right? This is the maximum possible current in the circuit. So the same thing is happening over here. This is your I naught, which is equals to E by R, and the graph goes like this. Okay, it will never touch this line. It will keep on growing like this. At certain time, which is basically t equals to tau. You remember tau? Tau from time constant.
Yeah.
The current becomes 0.63 times of E by R. Here in this tau is basically what? L by R. लिख लेना. So at t equals to tau, which is equals to L by R, I is equals to E by R into 1 minus e to the power. Do you remember it was t by tau, right? Or it was t by, what was the formula? Can you see the formula? E minus R by L into T, right? Yes or no?
Yes.
So the same thing we are doing again. This will be R by L into T. In place of T, you will write. In place of T, you will write
L
L by
by
R.
R.
So basically this and this and this and this will get cancelled. E to the power minus 1. This will be E by R into 1 minus e to the power minus 1, and 1 minus, this will be E by R into 1 minus 1 upon E. E is 2.71, and when you solve this thing, this current will become 0.63 times of E by R. That's why I told you that when time is basically this much, the current is basically this much. So how is the time constant defined? This is the time when the current becomes 0.63 times of the maximum current. Okay, so this
Yes, sir.
is defined as your time constant for RL series circuit. Yes, can anyone tell me what was the time constant for RC series circuit? The time constant for RC series circuit was what? R multiplied by C, if you remember.
Yes, sir.
So the same thing is happening over here, but just a little bit opposite. Okay. Acha, if I talk about after a very, very long time, after a very long time, which is, let's say, approximate kar rahe, 5 times of tau. The current is equals to E by R, and this will be 1 minus e to the power 5. This will be something like this, and when you solve it, it will come approximately 99% 0.99 times of E by R. So almost maximum, right? So this time is basically called as what? Transient time. So basically this is the time after which the steady state will achieve. the current almost becomes constant, and then we say this is the steady. There is a slight difference between both of them. So when you compare both of them one by one, hand in on the left hand side RC circuit, on the right hand side RL circuit, then you can understand the difference between both of them. Okay, is this
Yes,
clear,
sir.
guys? Check.
Yeah.
Please remember, at steady state, the current will be approximated to E by R. We'll say that it is the maximum current over here at steady state. There, are you done writing till here, guys?
So,
Hmm?
the T is equal to 5
Five,
2 or the
five.
approximate.
Ha. When
So,
T,
I didn't
so
understand that.
y is approximate.
Yes, sir.
Low. Let me make it equal. At t equals to 5 times, the current is equals to 0.99 times. Then we can approximate to E by R.
Okay,
Okay?
sir. Yes, sir.
इतनी डिटेलिंग पे ध्यान देते हैं बच्चे, मतलब देख रहे हो. Anyways, behavior of inductor during growth. Acha. At t equals to 0, I told you na, at t equals to 0, what was happening? Initial state, the current was 0 in the circuit. Yes or no? But it was tending to grow maximum. So basically, at t equals to 0, if the current is 0, that implies that inductor is resisting the maximum. Here, do you remember this particular thing? At t equals to this thing we already discussed, I think. मेरे को याद है थोड़ा सा. Admit. Hmm. Can you see over here? At initial stage, the current in the circuit is 0, but di by dt is maximum, right? Yes or no? At t tending to infinity steady state, where the current becomes constant and di by dt, the rate of change of current becomes 0, right? So this is how we are, taking this result. This is how we'll use this result in numerical problem. At t equals to 0, an inductor in between 2 points of the circuit will be considered as a open circuit. Why it will be considered as an open circuit? Because it is not letting the current to flow. Yes or no? So open circuit,
Yes, sir.
no current will flow over here. At t equals to t tending to infinity, basically steady state after a very very long time, what will happen? The current in the circuit will become constant, and when the current becomes constant, then the rate of change of current becomes 0. So the current will not change anymore, current is becoming constant. That implies this inductor behaves as a closed wire, short circuit wire. It's just normal wire, okay? Just a wire between 2 points, okay? So we just call it short circuit wire. एक note बहुत important, please remember, the capacitor was doing just the opposite of this. The capacitor was initially it was not letting any current to flow, but as soon as it was getting charged, then it was letting current to flow through it, right? So please remember, note, at t equals to 0 and t tending to infinity, at the initial state and the steady state, the behavior of inductor is just opposite of a capacitor. is opposite of capacitor. Guys, did your school start?
Yes, sir.
Yes, sir.
Yes, sir.
You people are going school now.
No,
No,
not
sir.
going
Through
school.
online.
Acha, still it's online. Will it be online?
Yeah, mostly.
Mostly it will be online. ठीक है? Okay. ठीक है, guys. Remember this thing. Initially, inductor behaves as a what? Short circuit wire. And steady state, initially it behaves as a open circuit wire, and after a long time, it behaves as a short circuit wire. ये थोड़ा सा इसका behavior देख लेना. We'll use this result in questions. Okay. Remember this. Then
Yes, sir.
to active inductor before this. Now, the second thing which is there is basically called as the decay of current. But before teaching you decay of current, I need to teach you something called as active inductor. What is an active inductor? Do you remember the charged capacitor thing? Guys, just give me 2 minutes. I'm getting one call. Yeah, hello guys. So active inductor. What is an active inductor? See, suppose whenever you have a inductor which through which a current is passing. Okay. So whenever you have an inductor through which some current is passing, do you remember this particular thing? There was a capacitor through which when charge was flowing, then charge was accumulating on the plates of the capacitor, right? What did you call this thing? What did you call this thing? Hello? Hello guys, can you hear me?
Yes,
Hello?
sir.
No one is saying anything. Can you hear me? Uh,
Yes, sir.
okay. So basically this thing which had a charge on its plate was basically called as a charged capacitor, right? And we know this particular thing, this charged capacitor was storing certain energy in it. half CV square or half Q square by C. This was the energy stored in the capacitor, right?
Yeah.
Yes or no?
Yes, sir.
Yes.
So this energy was basically, this charged capacitor was acting as a battery if you connected it in a RC circuit just across a resistor with no batteries and all. This thing was behaving as a battery, right? The energy which was stored in this particular thing was making it like a battery, right? The same thing is analogous with this. Active inductor is basically just same analogous to a charge capacitor. When you flow a current I through this particular, let's say if initially there was no current flowing through this conductor, we'll derive it, don't worry. So initially if there was no current flowing through this inductor, and at steady state, let's say a current I flows through it, then I can say the energy stored in this particular thing is similar.
Li square.
We'll derive this, don't worry. So this energy now, just like this charge capacitor, when it was connected to a resistor, it was flowing current. It was flowing current through it, right? The same thing.
Yeah.
Even this active inductor behaves as. Okay. I'll write it like this. Suppose if the current is cut out from a circuit, or just starts flowing. Tell me this particular thing. Okay, when, if there is a inductor in which some current is flowing, है ना? Or there is an inductor in which no current is flowing, and at one particular instant you switch on, will this happen ki the current will become infinity at the maximum? Within certain instant the current will become maximum. Does it happen like this, or does current grow gradually over time?
It
Right?
grows gradually.
Guys, I can't hear you. थोड़ी सी आवाज. Hello.
Hello.
Yes,
Hello.
I can hear you.
Okay.
So if the current is cut out from a circuit, or just starts flowing in a circuit, it can never become maximum to zero, or zero to maximum in an instant, right? Yes or no? Yes or no? That implies the magnetic flux through the inductor can never fall or rise suddenly. Is this statement making any sense or not?
Yeah, it makes sense.
It makes sense. Okay. So suppose just take this case when the current was initially flowing and then it is cut out. Okay. Then tell me, if suppose if I is the last current flowing in the inductor, then before cutting,
Sir,
yeah,
actually, it doesn't make sense, the sentence.
yes, sir.
Because, see, magnetic flux is B dot A.
हाँ,
And why can't we suddenly change the magnetic field?
तेरा B किस पे डिपेंड कर रहा है? On what factor does B depends?
The current.
And current is current depending upon time?
Yes.
So फिर,
Okay, now I get it. Yeah.
so if I is the last current flowing in the conductor, then before the current, then if now it's disconnected and then disconnected from the initial circuit, or you can say disconnected from initial circuit and then connected to some other circuit. The first current which will flow through the inductor will be same as this I, and this I is same. Are you getting my point, guys? The current, suppose I have one inductor over here, and in that inductor some current was flowing. Let's say I have cut this inductor suddenly and I have taken this inductor and put it into some other circuit. Then in that circuit, the first current which will flow through the inductor is basically the same I which was there in the initial circuit when we cut it. So it will never become zero in an instant. Are you getting my point? That energy will always be stored, just like a charged capacitor. Even if you disconnect a charged capacitor, that energy which is stored, the electric field which is there inside it, it will always remain. So you can use that as a battery sometime, right? The same way you can use a inductor as well. This type of inductor in which already there is some current stored or some energy stored is basically called as such an inductor. I'll write this thing completely. Now everyone understood what exactly is this? Guys, did you understand what exactly this active inductor is? It's just like charge capacitor. Such an inductor in which already there is certain energy stored. And which kind of energy, guys? Is called as an active inductor. So I'll connect this active inductor. Always remember, how is it represented? It is represented like this. There will be an inductor and they will just mention on this, over this inductor there is, let's say, current I naught. So what is the flux already stored in it? L times of I naught. Remember, flux is L into I. We have already discussed this result, I think, initially. Yes or no? This is an active inductor. So we'll see this, what exactly is this active inductor thing, and how is this active inductor related with the decay of current and all. Growth of current is done, active inductor is done. Now let's do decay of current. So once you're done noting this down, just tell me. Done, guys? Are you done? Guys, are you done with this?
Yes, sir.
Okay.
Yes, sir.
Heading Nalu, decay of current. Decay of current in an RL series circuit. Last year I didn't teach this to students because they wanted, sir, EMI, please teach us on school level. I said, okay, no problem. Decay of current in an R. What is happening? So suppose, guys, what exactly is the case? Let's say I have an active inductor in which what is the current initially? I naught, and I have given the direction as well, okay? And I have connected it to a resistor R, and let's say I have connected it directly to a switch. No battery involved, no nothing involved. Can you see any battery involved in this case? This is the scenario at t equals to 0. Okay. What is the current in the circuit? Is there any current in the circuit? At t equals to 0, I'll push this thing. Then what will happen? What is the first current which will flow in the circuit? What will be the first current which will flow in the circuit?
I not.
Now you got my point. What is an active inductor now?
It already has some energy stored.
Exactly. That energy got converted to just like a capacitor. Yes. Okay. Everyone understood active inductor now?
Yes, sir.
Okay. Now what will happen if I take it general? After certain time, what will happen? The current will start flowing through the circuit. This resistor will start dissipating certain energy. This inductor will start opposing the current flow, right?
Yeah.
When this resistor will be, so basically what will happen? The current in the circuit will start decreasing. So at any general time, if I say the current which is flowing through the circuit at any general time t, if I say the current which flows through the circuit is I, here at t equals to 0, what is the current flowing in the circuit? I naught is flowing. But when this current starts flowing, automatically it will start decreasing, and then this inductor will try to change that particular. So at any general time t equals to t, let's say the current in the circuit becomes small I, general current I, right? I'll close the switch, don't worry.
And sir,
Anji,
to maintain law of conservation of energy, the energy that's dissipated will be released as Joule heating, right?
yes, it is. It is releasing from the resistor, right?
Yeah.
Okay.
Hmm.
So is this clear, guys? At any general time, the current becomes what? Right? Can you apply Kirchhoff's law at this particular place? Can anyone apply Kirchhoff's law? Let's start from here. Am I going in the direction of current or in the opposite direction of current?
In the direction.
The direction.
In the direction of current. So in the direction of current will be minus of L into di by dt. Yes or no? Negative?
Yeah.
Enough. Then I am going again in the direction of current, plus or minus?
Minus.
Minus I into R. Yes or no? And then I'll come back through this switch to again this point. So basically this will be equal to 0. Yes. So
Yeah.
by Kirchhoff's voltage law, is this equation will be forming. Now I'll just separate the term. I'll move this IR on this side. So R into I is equals to, can I move this L also downwards? Guys, can I move this L on the right hand side in the denominator?
Yeah.
Also with this minus sign, can I move it over here? This will this be di by dt?
Yeah.
Then can I move this I in the denominator of this and dt over there?
Oh, so you're going to integrate it.
Exactly. So minus R by L, and then I'll do what? I'll just integrate it. Okay. So when time was 0, what was the current in the circuit?
0.
Acha.
I not, sorry.
I naught. And when time was t, what was the current in the circuit? I.
Small I. Yeah.
Are you getting my point? How do we use maths and physics together? How do we describe the limits? We
Yeah.
think of the limits, we put it in the integration. Simple. Integration is just a tool. सोचना बाकी का पूरा physics में पड़ता है. Okay? So कर दो integration. बचा क्या जीवन में? Di by I is ln of I, and the limits will be from
I naught to I.
and here it will be minus of r by l into dt. In the limits will be,
That's just T.
so basically when I solve this thing, this will be ln of I upon I naught. This will be this will be ln of I upon I naught. Yes or no? Ln I minus ln I naught, which will be ln I upon I naught. Yes, it will be equals to
Yes, sir.
minus of r by l into t. I'll shift this over there, it will become e to the power, and then I naught over there will become e to the power minus r. Sir, this relation also looks similar. Is this the same charge relation during the discharging? You remember RC circuit discharging, Q is equals to Q naught into e to the power minus r by l or t by RC.
Yeah.
Same thing.
Hmm.
Okay. So can you see everything is similar? Because I told you, nature is symmetric. Electromagnetism was very symmetric. That's why electricity and magnetism were merged together under electromagnetism. Okay. So this is how your current is decaying. Where I, this I is basically the general current at a general time t. Yes or no? Any general time instant. Where what is I naught?
The current at T equal to 0.
Exactly the initial current in the inductor, or basically in the active inductor. Yes. Is this clear? Please note it till here. Then we'll do the note, we'll do the graph, we'll do the time constant again. And then
Sir,
we'll do some. Haan, bolo.
So it's like just a hypothetical question. Why can't the current like flow at the same value like till T equal to infinity? Why is there a decay?
Because the inductor over there, the resistor will do what? The resistor will start dissipating certain heat, due to which certain current will increase. There is no energy providing source now. Is there energy providing source in this case? In the previous case, it was battery. Is there energy providing source in this case? Constant source of energy.
Okay, so inductor can't provide a constant source of energy. It can
Now,
provide a source of energy, but it's not constant.
हाँ,
It depends.
तेरा मोबाइल का चार्ज कैपेसिटर जो होता है, मोबाइल की बैटरी खत्म क्यों होती है? तो इस हिसाब से तो खत्म ही नहीं होनी चाहिए.
And if the same circuit had a battery, the current would be constant till T equal to infinity.
The current will become constant, but you know what will be the only difference? Suppose guys, in the previous case, when we discussed the growth part, this part, do you remember this part, guys? Growth of current.
Yeah.
This one. So initially, in place of this inductor which has no charge, no current in this, if I would place an active inductor over here, and then what will be the only difference in this case? This thing. Can you see over here? This thing will not be zero.
It will be I naught.
Exactly.
For an active inductor.
So basically, what will the only change which will change is basically what? The limits. The only thing which will change will be the limits, and accordingly you will solve, and then you will get some other term. Okay. The formula will be different. This is only when the initial current through the inductor is zero. This is only valid till then. Just like an uncharged capacitor. If there would be charged the capacitor, then the limit would change. नीचे क्यों not लिख दोगे? Right? So this is how you do it. Any doubt?
No.
Okay. Everyone, any doubt? I know thoda sa things are more on the mathematical side, but physics and maths is just like brothers. Without maths, physics is not there. We cannot explain it. So even if you are a bio student, still A little bit physics will require integration, differentiation at least, and बाकी का physical significance तो I'm there to make you understand, right? Is this clear, guys? So this is your formula. Hanji.
Okay, so when you say that you charge a capacitor, right, and then suppose if we take that charged capacitor out and we place it in parallel with any other component, so you say that the capacitor acts like a battery. So if it follows the same rules after some t, like some time t,
the current becomes
it will
zero.
also deplete in energy.
The resistor depletes some energy, no?
Okay, what if I connect it to a bulb? Will that still happen?
Yeah, a bulb is nothing but R only, no?
Fine. Okay.
Chala. So I think this is pretty much clear. Please write a note. As I naught starts flowing at t equals to 0, heat starts producing in the circuit. Due to which what will happen? The value of current
decreases.
That implies I will be always less than the maximum value. The instantaneous value will be always less than the maximum value. And if I draw a graph, the graph will look like this. Let's say this is the maximum value, and from here, just like discharging, it will never become zero, by the way, na? When will it become zero? It will become zero at
t equal to infinity.
Or basically we generalize t equals to infinity as basically the 5 times of the time constant. So here also we'll define the time constant. Time constant will be basically what? The same thing, R by L. So at time t equals to R by L, which is basically defined as the time constant for this, the current will become I naught. Acha. What was the formula? I is equals to I naught into e to the power minus R by L into t. So we'll put t equals to, sorry, R by L into t or L by R? Oh, it will be L by R, no? This time constant will be L by R, no?
So why?
अरे तभी तो कटेगा.
Oh, yeah.
Here also it was L by R.
Yeah.
So why is it like that?
Because then only it will become e to the power minus 1, no?
Okay, sir.
L by R, time constant L by R, right? So I will be I naught into 1 minus 1 upon e. We'll put L by R over here. L will cancel with L, R will cancel with R, e to the power minus 1, which can be written as 1 by e. And then 1 upon e is nothing but 0.37 times of I. Okay? 37% to the 63% है, इधर 37% है.
So everywhere it should be L by R.
हाँ जी बेटा. L by R, the time constant in RL series circuit is L by R. In RC circuit it is RC, R multiplied by C, right?
Okay, sir.
Here the R comes in the denominator, there R comes in the numerator. At t tending to 5 tau, I will be approximately, or you can write approximately नहीं, ना फिर questions आएंगे. I will be 0.01 times of I naught, and which can be taken as 0. Yes or no?
Yes.
This will be the complete decay. We'll assume completely current has decayed over here. So anyways, Clear, guys? Shall I start giving you questions?
Yes, sir.
Sorry. Eta times the maximum value of current, where eta is a fraction. Okay, eta is basically a fraction. I'll tell you eta lies between. Okay, so this is your series circuit, and you need to basically find the time in which the current will become eta times. This is the switch and this is the battery. For the current to grow, the battery should be there. This is E, this is R, this is L, and this is the switch which is closed at T equals to 0. Yes. What is the only thing which is given in the question? The only thing which is given in the current is basically the instantaneous current, which shall be what? It shall be eta times the maximum current, right? Yes or no? This is the only thing which is given. Now you need to
Yes, sir.
You need to find out the time when this thing will happen. The current will become the maximum. And give me 2 minutes. I'll just be back. Done. So basically, you just need to apply the formula. We know I, the general current, is basically I naught times of 1 minus e to the power t by tau, right? And what is tau?
L by R.
L by R. So it will be R by L into T. Acha, by the way, na, this was e to the this thing. I told you na, T R by L is basically 1 upon tau, right? If L by R is tau, then 1 upon tau is basically R by L. So I can write this R by L as 1 upon tau as well. So this same formula I can write it as I equals to I naught into 1 minus e to the power minus t by tau. The same formula I can write for this thing as well, RC circuits as well. Do you remember Q is equals to Q naught into 1 minus t by
RC. Yes,
RC.
sir.
So I can write RC as tau, so minus t by tau. Same thing. Anyways, करो अब तो करो solve. I naught and I naught will get cancelled, and this one will go over there, or this thing will go over there. So e to the power minus r by L into tau is basically 1 minus tau, right? And then you send this over there, it will become ln. So ln of 1 minus eta will be minus of r by L into t, minus sign. When it will go over there, it will go in the power of this. Okay, so it will become r by L to t should be equals to ln of 1 upon 1 minus eta, and then this ln r shall be multiplied. Khatam. That's the answer. Okay, this is the answer. Shall I give you one more question?
Yes, sir.
This question is homework. Same similar type but in decay. Okay, during the decay of current in an RL circuit, series circuit, if the current falls to eta times the initial value, and obviously this eta will be less because it is falling to eta times, right? But here this eta वैसे करना पड़ेगा, same thing. It is falling है ना, ध्यान रखना थोड़ा. So basically you will use अच्छा sorry. Don't try it ना, अभी रुको. Okay, so it is falling in time t. So basically I have given you this time. Okay, this time is given as capital T, and you need to find what is the value of time constant. Same type of question, but just the formulas will be different. The answer should be T is equals to, oh sorry, something like this. And why I've used mod, so that it will be clear कि n is should be between 0 and 1. There's no need to use the mod, but कर दिया. चलो, next question.
So
Anji.
I'm confused how where it should be L by R and where it should be R by L.
The tau for RC circuits should be RC, है ना? And here the tau should be L by R. And when you'll use the formula, you'll use 1 upon tau, right? The formula for I equals to I
Yes, sir.
naught into 1 minus e to the power minus t upon tau, right? So 1 upon tau is basically R by L. So R by L you will multiply with this.
Okay, sir. Understood now.
चलिए एक क्वेश्चन दे रहा हूँ. The switch is closed at t equals to 0. Now the question is find the function of current with respect to time. See, if it would have been a normal RL series circuit, then what would have been your answer, guys? If this circuit was just like this, inductor and a resistor, sorry,
So I is equals to I naught e
connect
1 minus e to the power minus t by tau.
once more. क्या?
We have to find that current wala thing only, no?
हाँ, find the current in the inductor as a function of time.
Okay.
If this would have been the case, then your answer would have been what? I is equals to
I naught 1 minus
I naught. What was I naught? Was I naught E by R
e by r, yeah,
into 1 minus e to the power
e
minus,
to the power r by L times t.
है ना? So if this circuit would have not have been given, and if it would have been only this circuit, the answer is simple then. Yes or no?
Yes, sir.
So फिर what to do now? Can I convert this circuit to this circuit by some method?
Series parallel.
No. I think I taught it in current electricity.
Do we use loop law?
No. We use Thevenin over here. Can you see over here? There is an equivalent battery. There is a battery over here and a resistance over here. So equivalent battery across this inductor, right? So basically remove this from here. When you remove the inductor using Thevenin's method, and that's why I taught you lots of methods, because those methods will not be only solving your current electricity problem. They will be solving a lot of different things. Okay, that's why we focus too much time on current electricity. So basically this will be your E, this will be your R. There is a switch over there. Let the switch be over there. There is R over here, and there was one more R over here, and we have removed the inductor, right? Was this the circuit left without the inductor? Will this be the circuit
Yes, sir.
without the inductor? Yes or no? So let us say the inductor is connected across X and Y. Tell me this particular thing. When I remove the inductor, is there any current flowing in the circuit?
No.
Yes.
In R, I thought in R, no current will flow, right?
No, in this R, no current will flow, but through
Yeah.
these two R will be the current will be there. There is one
Yes,
closed
sir.
loop. So current will flow only in this. And what will be the current in this? Can you see this R and this R in series? Yes or no? So our net will be equals to what? 2R, and the current will be E upon 2R. This will be the current flowing in the circuit when this inductor is being removed. Yes. Yes or no?
Yes, sir.
Can you give me what is the potential difference between point X and Y? So Vx, let's start applying open circuit Kirchhoff. Is there any current?
No.
No. So basically minus R into 0. फिर उसके बाद I'm going, can you see I'm going from X to Y? So plus IR minus IR. I'm going in the opposite direction.
Plus IR.
Plus IR. And then we'll go to Y. So this is equals to Vy. So when you solve it, can you see over here Vy minus Vx? Can you see? This thing will become 0. This is plus IR, so I have to shift this Vx over there, and this is equals to IR. Anna? So which potential is greater? Vy is greater. Yes. So this is basically the first step in which I calculate this will be acting as my E equivalent. Now I just need to find out what is R. Yes or no? R equivalent. Yes or no, guys?
Yes, sir.
So I'll draw the same circuit but without batteries. Everyone forgot about the Thevenin's method, right? I guess. सब भूल गए. We don't draw the battery anymore and we just draw the resistors and we try to find out what is the resistance between X and Y. No battery drawn. Yes. Can you tell me what is the resistance between X and Y? Can you see this R and this R is in parallel or series? This R and this R is in parallel. They are in parallel. Why they are in parallel?
Because current divides.
Because when the current will start flowing between Vx and Vy, some current will come over here and then it will divide at this point between here and here. Current is dividing, hence this R and this R is in parallel. Then this current will flow through this R, come back through this route. This current will flow, they will become merged again and then reach Vy. So basically this R and this R, I'll use a different color. So ये और ये parallel में है, and whatever is the combination is in series with this R. Yes or no? So what is the R equivalent? R equivalent will be this R plus R and R in parallel will be R by 2. So 3R. So R equivalent across XY is basically 3R by 2. E equivalent is I into R. Yes or no? And what is I? E by 2R multiplied by R. So can you see over here, guys? E equivalent is E by 2. R equivalent is 3R by 2. So I can make the whole circuit again. I can just make a resistor R equivalent, which is 3R by 2. I can connect E equivalent, which is bigger, by the way. Vy was bigger, no? So positive terminal towards Vy. And this is X. And then now I'll connect the inductor. So can you see I converted the whole circuit to just an LR series circuit like this. And now I know the formula. I know I is equals to E by R into 1 minus E to the power R by L into T. So I just replace everything. So here the answer will be, what is the E equivalent in this case? E by 2. So hence E by 2. What is the R equivalent in this case? 3R by 2. So hence 3R by 2. Are you getting my point, guys? What exactly am I doing? 1
Yes,
minus
sir.
E to the power minus R. R will be again 3R by 2. L will be L only and T will be T. So basically the function of that circuit will be this. Hence this is your answer. And you can solve it further if you want. No problem. Okay. So these questions, they are very important to your JEE NEET point of view. Okay. Is this clear, guys?
Yes, sir.
Please remember, tell me this particular thing, guys. If I have pure inductive circuit, so for pure inductive circuit, I'm not discussing the whole thing. I'll tell you the result. For pure inductive circuit, like for example, there are some inductors which are in series and parallel connection, right? So the same logic which you used for resistors, you'll use the
Resistance, right?
same thing. You'll use the same thing. Okay. So you can write note series and parallel formulae. For pure inductive circuit is same as those for Anji. What is the equivalent inductance of the circuit? What is the equivalent of the inductance of the circuit? It will be L1 plus L2, just like R1 plus R2.
Yeah.
Same thing. And same goes for parallel connection as well. So remember this: if you have pure inductive circuit, then always do it same as resistors. Capacitors may we do the opposite, right?
Yeah.
Yes, sir.
Here we have to do the same. So I think the questions is clear. Shall I give you some more? Guys, shall I give you some more questions based on Thevenin circuit?
Yeah.
Yes, sir.
You can take RC circuit questions as a reference, okay?
As a what?
RC circuit questions as a reference. If you get
Okay.
stuck, okay, what did we do in this thing? Then you can take those as a reference. Okay. Now the question is, find the current through the battery. Find the current through the battery first at t equals to 0 and second at t tending to infinity. Please remember, t tending to infinity is called a steady state, and I told you how exactly an inductor will behave like. Okay, at t equals to 0 the inductor will behave like a open circuit, right?
Yes,
Yeah.
sir.
So basically there will be open circuit, no current will flow through over there, so r will be 2r. Okay, and
E
hence
by
the
2R.
current will e by 2r, and similarly you will do for t tending to infinity. Okay, chali. One more question as a homework, and that will be it for today's class.
Sir, I had a doubt. So
बोले?
could you spare extra minutes after class for that?
तो एक काम करना, मेरे को फिर तू 8 बजे के बाद कॉल कर लेना.
Okay.
चलेगा? हाँ, मतलब अभी जैसे if I'll be leaving after this, then you can take those 7 minutes. No problem.
Okay, sir.
क्योंकि अभी नया टॉपिक स्टार्ट करने में वो खत्म नहीं होगा फिर, because I need to start with energy stored in a conductor, then magnetic field energy density, some questions. नहीं, ऐसे questions की there is no need for this, but हो जाएगा. And then I need to do mutual induction. So I think in the next class I will be done with LC oscillation is also there. There is transformer as well. There is one more thing left.
So doesn't transformer come in AC?
But I think I have the wrong page over here. ठीक है, तो फिर मतलब ज्यादा नहीं बचा है, 1-2 लेक्चर में दिस चैप्टर विल गेट ओवर. In 1 or 2 lectures, we'll be done with EMI and we'll start with magnetic effect. No, sorry, what was that chapter? Magnetism and matter.
Oh, okay, that one.
So most probably I'll be giving you notes for the same. It's a complete theoretical chapter, so we won't be discussing just like this one note thingy. We'll be discussing it on like PDF and all. It's a theoretical chapter, no. Whatever numerical part will be there, we'll be doing it over here. Don't worry. So I was giving you a question. Six ohm, 3 ohm, 20 volt, 2 Henry. 4 ohm. So question is again, find the current in inductor as a function of time. So whenever I'm asking as a function of time, that is basically what I need to use, what Thevenin over here, right? Because I need to convert this to an equivalent battery and use Thevenin. So I'll write the hint as well. If you have forgotten Thevenin, please don't do that. Chal, that's it for today. In the next class, we'll see active inductor, magnetic field energy density, mutual induction, some questions. Okay?
Okay, sir.
Chalo, theek hai, okay.
So I can call after 8, right?
Haan, theek hai, no problem.
Okay. Thank you, sir.
Chalo, thank you very much.
Thank you, sir. Thank you, sir.
Okay.